finish up.
Hello, my name is John Goss. I'm the former president of the Astronomical League and part of the league's 75th anniversary committee. We are doing another number of things for this event for our 75th year, which actually is on November 15th, 2021. We are featuring a number of programs throughout the year on various topics. Many of them are on our observing programs, such as comets or binocular objects or radio telescopes or deep sky observations, things like that. We have other programs coming up which will be discussing our awards series, such as our Youth Awards, which are the NYAA Young Astronomer Award, the Horkheimer Service Awards. We have a new award coming up this year called the Williamina Fleming Award. It's for imaging. You'll be hearing more about that. And I'm glad you're all joining us, because I want to give some special recognition to one of our committee members, Peggy Walker, for arranging all or most of these programs and getting it all together, getting people, arranging for people and times and all that. So that it's a lot of work to get done, but I'm glad she did it for us. Today, I'd like to introduce Carl Hergenrother, who is our co-coordinator for the Target NEOs program, and he's here to talk a little bit about comets. Carl works at the University of Arizona, so he's coming to us from Tucson right now. I guess it's from Tucson, isn't that right, Carl?
Yep, it's Tucson.
Tucson, all right. So what I'd like to do is turn it over to him, and he can tell you a little bit about what he's going to do, and then he'll tell you what he's going to do. Carl, it's all yours if you'd like.
Okay, thank you. And I'm actually going to share my screen because I've got some slides to present, if that's okay.
Okay, you should be ready now.
Okay, let's make sure this works. And is everything looking good?
It looks good. There's a comet in there, and there's a bright planet, and ready to go.
Okay, great. Yeah, so thanks for having me. And it's a thrill to be here and to actually talk to everyone in the Astronomical League and out on the internet about comets. So just to give an overview of what I'm going to talk about, this is going to be a lot of why do we observe comets? What are comets? Why do we observe comets? And how should we observe comets? And what kind of observations can, amateur astronomers with, modest telescopes. We all don't have 5-meter telescopes in our backyards. Most of us don't, at least. And can these observations still be useful? And where do you send such observations if you want to kind of do more scientific sort of observations? So just a little bit about myself. As John said, my name's Carl Hergenrother. I'm both an amateur and a professional astronomer, mostly specializing in the observation of comets and asteroids, so kind of the small critters of the solar system. And I've done a little bit of everything with regard to comet and asteroids. I've been involved with discovery. I used to work at the Catalina Sky Survey, which is one of the 2 or 3 premier NASA ground-based asteroid and comet surveys. And during my time at the Catalina Sky Survey, I was able to discover 4 comets. So 3 of them have my name attached to it. So kind of like David Levy, who's also giving a talk this month about comet discovery, I've also discovered comets, which is pretty cool. And I've got to see 3 of them visually, though I did have to cheat and use a 1.5-meter telescope to see one of them. And most recently, I've been working on the OSIRIS-REx mission, which is a NASA-funded asteroid sample return mission that just collected its sample back at the end of October. And we'll be heading home soon, and the sample will return in 2023. And I think actually in April, during the asteroid month for the Astronomical League, I'll actually be talking a little more in detail about the OSIRIS-REx mission. On the amateur side, my favorite telescope is actually my pair of 30 by 125 binoculars. They weigh 22 pounds, but still I've got my tripod outside. I wake up, I stick them on there, I observe my comet, I'm back in bed within 10 minutes. I love those things. On the professional side, I really can't do much better than the Vatican telescope, the 1.8-meter VAT, which is up on Mount Graham. Subarc second seeing, nice field of view. You can see down to 23rd magnitude. That was my favorite professional telescope, and just a great location to observe from. And also, I've been involved in quite a few kind of citizen science or amateur professional type organizations. Most relevant to this talk is I'm the coordinator of the ALPO, the Association of Lunar Planetary Observers Comet section, and also the co-coordinator of Target NEOs, which is an observing program at the Astronomical League, which actually was an outgrowth of a citizen science program that Dolores Hill and I were running at OSIRIS-REx called Target Asteroids. And in addition to these, I'm also on the board of directors for the American Meteor Society, the AMS, and an editor for the International Meteor Organization. So I do a lot of meteor work too, or at least used to. I've kind of fallen off a little bit lately. But let's go back to comets. So what are comets? Well, simply, comets are small solar system objects that have a lot of ice, a lot of what we call volatiles, material that you don't have to get it very hot and it starts sublimating, it boils off, and that process will actually carry other ices, gas, and dust with it. And it creates kind of the telltale sign of a comet, which is a cometary coma, which you can see here, and the tails that go off. And here we've got a nice picture of, and I'm not sure you can see my cursor, but it is moving around. You can see the nucleus of short period comet 103P Hartley 2, and you can see the gas jets blasting off there. Now, there are a lot of different kinds of comets, and we usually categorize comets based on their orbits, what we call a dynamical classification. You know, we have short period comets, which are comets that orbit the sun roughly once every, say, 5-6 years, and they usually don't get much further out from the sun than Jupiter. There are long period comets, of which there are a bunch of different varieties, but some will go out almost a significant fraction of the way to the nearest star, Proxima Centauri. So these are objects that go out almost half a light year, maybe even a light year away, and they come from the Oort cloud. And then we have a few kind of intermediary objects. Like, for example, there's a class of objects that sometimes show cometary activity, sometimes not, but we call them centaurs. And these are objects that we think actually have migrated in from the outer solar system and are now bouncing around the outer planets and have not quite broken into the inner solar system. But the thing is, where did all these objects come from originally? Well, the current thinking is that when the solar system formed, and you had that primordial disk that then collapsed and created the planets, as well as the planetesimals or cometesimals, the little pieces that were left over, all of the large planets were much closer to the sun than they are now. And now we have, Neptune that's just sitting out almost at 30 AU. But back in those days, everything was within about 15 AU. And you had a pretty dense belt of cometary material that was sitting out 15, 25 AU or so. And then maybe about a half a billion years after the solar system formed, things went a little crazy and haywire as the outer planets started moving in and out and fell into resonances with each other. They disturbed this cometary belt, threw a lot of mass, cometary mass, completely out of the solar system. So now these are going to be the Comet Borisovs and Oumuameas of another solar system, as well as a bunch of comets that were thrown into the Oort cloud. And eventually those Oort cloud comets will fall back in as long period comets. Just outside the orbit of Neptune, they call either the Kuiper belt or the trans-Neptunian object population. And those are the objects that over time become centaurs, bounce around the outer planets, and make their way into the inner solar system, where they are short period comets. But are all comets really comets? We have a lot of objects out there that look cometary, kind of like if it quacks like a duck, if it looks like it's a duck, it's a duck. But we have an object like, take this one up here at the top, P2010A2, as well as an object like Sheila. Those actually aren't comets. They look like comets, but what we're seeing, this tail, is actually a result of an impact of another body into the main asteroid. And as a result, we're actually just seeing the debris of that impact spreading out. So those objects really aren't comets in the traditional sense. And there's a lot of different mechanisms that we're now identifying, like impacts, rocks simply fracturing in the heat, minerals thermally dissociating as they heat up and you're driving off volatiles within it, and other things that actually can appear to produce what looks like cometary activity. And for something that hits really close to home for me, one of the first surprises of the OSIRIS-REx mission, and this happened only a week after we dropped into orbit, so this was like the first week we were really close to the asteroid, we discovered what looks like hundreds of particles being blasted off the surface of the asteroid. And it took us a while to figure out what's going on, and we're still not 100% sure, but we think this is probably the result of meteoroid bombardment, and not even large meteoroid bombardment. Here on Earth, when a meteoroid hits the upper atmosphere, it looks like a meteor. It's great. 80 kilometers up, burns out, puts on a nice light show. When you're an object that doesn't have an atmosphere, that meteoroid just hits the surface at velocities up to many tens of kilometers a second. And actually, it's quite energetic, and it throws all these pieces off. So not everything that looks cometary or releases comet mass is actually a comet. For example, here's this beautiful picture of the nice, multi-degree long comet tail of this fairly bright object sitting nearby the Pleiades. But in fact, that is the planet Mercury. And that is a sodium tail that was imaged by a coronagraph at the McDonnell Observatory, showing basically what happens is you've got solar wind and meteoroid bombardment on the surface of Mercury. It does what we call sputtering, which is kind of fancy word for it just kicks stuff off the surface. And then the sodium actually gets ionized and blown away by the solar wind, and it creates this nice tail. And it turns out a lot of amateurs now with a nice, narrowband sodium filter can actually image Comet Mercury every time it's at, maximum elongation. But let's get back to the more traditional comets, the ones we all know and love. Why should you observe comets? In a way, because comets are probably one of the most dynamic objects in the night sky. I mean, they move just like planets and asteroids. They change brightness just like variable stars. They're extended objects like your favorite globular clusters, your favorite galaxies, and they're unpredictable. They can outburst, they can disintegrate, they can show jets. It's like rolling, the fun of observing all these different kind of astronomical objects into one. And that's one of the reasons why I'm always drawn to comets. And it probably isn't a surprise that in addition to comets, I do like observing variable stars, supernovae, novae, meteors, things that change. So just to kind of go through, what are the sort of observations that you can make? Well, the simplest is what we call astrometry. And astrometry is really just measuring the position of an object on the sky, measuring its right ascension and declination. And of course, comets are in orbit around the sun, so they're moving. And there are a lot of programs out there that will allow you to measure your CCD observations. This unfortunately isn't a type of observation that you can do visually, at least not anymore. You could have done that 150 years ago, not so much now. But using CCDs, there's a lot of programs out there that are reasonably inexpensive and sometimes even shareware that can allow you to measure the position of a comet. And you would report those positions to the Minor Planet Center. Now, the thing is, you don't need an especially large telescope to do this. Now, yes, there are lots of surveys out there like ATLAS, like Pan-STARRS, like the Catalina Sky surveys that are covering the entire sky down to 20-second magnitude, almost nightly. And they're getting a lot of these objects, but they're not getting all of them. And even in the future, when we have stuff like the Vera Rubin, the old LSST, or NEOSIM, which is a space-based infrared camera that hopefully will be launched in the next 5 years, they will be observing a lot of these objects too. But remember, Vera Rubin is a giant telescope. It's saturating most objects that are brighter than about 16th magnitude. So we could find a time in the future where it's large surveys that are covering the sky back and forth every night, but they're really trying to get that 24th magnitude object. And so the really bright objects will fall to the smaller equipped, the observers that are equipped with smaller telescopes to do a lot of work from the backyard. And of course, the astrometry you produce is used by organizations like the Minor Planet Center to update the orbits of these objects. Otherwise, they would get lost. Unlike planets where you know where they're going to be for centuries in advance, even asteroids, after you followed them for about 10 years, you pretty much know where it's going to be for the next century. But comets, of course, have jets. They've got, basically geysers blasting off the surface. And these are fairly small objects, maybe sub-kilometer to a few kilometers. So their orbit's actually changing quite a bit just due to these, what they call non-gravitational forces, as well as the fact that the reason why comets are even here is because they get close enough to planets to be thrown into the inner solar system. So they quite often will make close approaches with planets like Jupiter, and their orbits can change quite dramatically. So as a result, most comets do need relatively often routine astrometry to update their orbits. And there's other things that you can actually learn science-wise from comet orbits. For example, those very forces I was just talking about, those geysers, these non-gravitational forces, also change with time. And you can measure that by, basically collecting everyone's astrometry and noting little changes in the position of the comet that kind of deviate from just pure gravitational motion. Or if you have an object that disintegrates, and we've had a few recently, we all remember ISON back a couple years back, as well as just last year, we had Comet Atlas, which was supposed to be the comet of the decade, and then it disintegrated. You can actually look at the astrometry and start noticing when the position of the comet starts deviating from its prediction. And you can kind of tell from that point that the nucleus has disintegrated. And actually now it's solar radiation pressure, that's solar wind that's blowing those particles backwards and away from where the position is supposed to be. Other thing you can produce is photometry, which is really just measuring the brightness of a comet. And this is something you can do even without a CCD. In fact, this is probably what most of my observations now are just going in the backyard, like I said, my 31 by 125 binoculars, unless the comet's bright, and then it's just my 10 by 50 binoculars. And I go out there and I measure how bright I think the comet is. Now, measuring a comet's brightness is a little bit tricky. It is similar to how you would measure the brightness, say, of a variable star. Of course, the problem here is you're comparing a diffuse extended object with your reference stars, which of course are stars, so they're point sources. So you usually have to use a bunch of different techniques, and that kind of also depends on just how condensed or small or large or diffuse the comet is. But there's a bunch of different techniques that can be used for, say, defocusing a star and then comparing the defocused image with the comet. You defocus it out to the same size as the comet and you compare. There's other kind of hybrid techniques as well, where you maybe defocus the comet a little bit and then defocus the star out to that size. Or in the case of Comet Neowise, when it was really close to the sun, it was almost like a point source itself. So I know in my 10 by 50 binoculars, I could just defocus both the star and the comet at the same time, and you get a pretty reasonable estimate of how bright the comet is. Of course, you still have to watch out for certain little gotchas, like in the case of Neowise, this was really important. Most of us, especially that first week or two when Neowise popped out of the sun's glare, was, at super high air mass. And so it was at usually a different air mass than what your comparison star was. So you have to correct for those things. And because comets are most part reflecting sunlight, you want to use stars that have similar color to the sun. But other things that you can measure just with visual observation, of course, is the size of the coma, what we call the degree of condensation, and I kind of show this here, just how diffuse or condensed is it. If it's a complete fuzzball that doesn't even look like it has any central condensation, that would be a degree of condensation, a DC of 0. On the other hand, if the comet looks almost stellar itself, in some cases it is stellar because it hasn't turned on. And for people who have large Dobsonians, sometimes you can even visually directly observe a comet's nucleus before it's actually become active, and it looks like a star. CCD imagers can do this quite often, especially if you can get down to like 19/20th magnitude. You can catch some of the Jupiter family comets before they turn on and then after they turn off. And then, of course, just measuring the length and position angle of any tails. And towards the end of this talk, I will actually list a bunch of organizations that either you can go for more information on all these various observing techniques, and that you can also contribute your observations if you wanted to. And of course, that also includes the ALPO. So say you're an imager and you want to do photometry with a CCD or CMOS. that allows you a lot more flexibility than visual. For one thing, you can measure the entire coma of a comet, but you can also measure, say, just the innermost part of a comet. And it's kind of interesting because there are people who do both or do one or the other. When you're measuring the entire coma of a comet, what we call the total magnitude, what are you really seeing? You're seeing dust that was released over time that's building up in that coma. And in the case of some comets, like some of these new, dynamically new comets, long period comets, these are comets that haven't been through the inner solar system before and appear to be really active when they're far out. And these are the comets that quite often will head fake us into thinking that the comet will end up becoming the comet of the century. Kohoutek was a dynamically new comet. Those of us who can remember the 80s, Comet Austin back in 1990 was a dynamically new comet. And of course, ISON most recently was also a dynamically new comet. Sometimes those comets are releasing dust, and we knew this in the case of ISON, as far as 20 to 40 AU out. So out, orbit of Pluto. So when you're measuring that coma, you're seeing dust that was released over years of time. Now, if you only measure the brightness of the innermost coma near the nucleus, you do a better job of measuring, maybe you could kind of call it the instantaneous comet's production. What is the most recently produced dust that was released? And so a lot of people will actually only measure this little inner area of the coma and measure a parameter that's called AF rho. And that really gives you a better indication of how active is the comet now, because you're only seeing dust that maybe was released over the last hours or days, rather than the entire coma, where you may be seeing dust released over days, weeks, months, or even years. Of course, one thing to remember when you're doing CCD photometry of a comet, quite often, in order to see the entire extent of the coma, you really have to stretch your images to the point, like this image here, it looks aesthetically ugly. But that's the only way you realize that instead of this nice picture here, where you only see a little bit of the coma, and here you can do a little log stretch, the coma itself really is a much larger beast there. And then you have the added complication of, if you're measuring everything within the circle, boy, there are a lot of stars in there. So there are little gotchas you have to learn. Like anything, it's kind of a art in a way more than the science. But yeah, for the first, I'm surprised I got this far before I blanked. Let me regroup. So it's similar to the visual photometry. CCD photometry is also a little more of an art rather than a science. And there's lots of little gotchas that you have to take into account when you actually try to measure the brightness of a comet. So what does the brightness of a comet actually tell us? Well, for example, light curves. This is actually the light curve of Comet Neowise, our favorite comet from last summer. And it actually shows why Neowise became the bright comet it was. When Neowise was discovered, it was nothing special. It was about a 19th, according to the Neowise spacecraft, it was about 19th magnitude. Once ground-based CCD observers got on it, they realized it was a little brighter, but it still seemed like a fairly runty comet. And in fact, it looked like the kind of comet that, for object getting that close to the sun, might even disintegrate. But what happened was the comet rapidly brightened. For whatever reason, maybe it was an outburst, maybe just new areas on the surface became active. And then it started brightening at a rate that was a little higher than what you would call average for a comet. So we've got this nice little comet magnitude formula. I'm not going to go into all the math, but this 2.5 n log r, that is the rate at which the comet brightens with respect to its distance from the sun. Now, usually, traditionally, for a long time, comet scientists would, if a comet was discovered, they would say 10 log r. And that's led a lot of these comets I talked about before, a lot of the predictions astray, because your dynamically new comet making its first trip through the inner solar system, usually this is a lower value. It's like 7 or 8. And if you use the average value of 10, you end up extrapolating a comet that is way too bright when it's at perihelion. But if the comet has been around before and is what we call dynamically old, or even a short period comet that we know has been around multiple times, this number could be much higher. It could be 10, it could be 15, it could be 20. So what really kind of surprised us with Neowise was it was about 12 for all the way in. And of course, Neowise was behind the sun for a good chunk of that time, so we weren't really able to monitor it. So it was a little bit of a surprise when all of a sudden the sun-watching spacecraft saw Neowise there at 2nd magnitude, and then it popped out in the morning sky at about 1st magnitude. But if it had brightened at, say, an 8 log R rate, it wouldn't have been a very, I mean, it would have been a nice comet, but it wouldn't have been the comet the best comet we've seen in the Northern Hemisphere for over 20 years now. So I said, comets are extended objects, as we all know. And there are quite a few things you can observe, even visually, near the nucleus of a comet. The two images right here, one is of Hale-Bopp, and that's over on the left. That was taken back in, of course, 1997, when Hale-Bopp was, the comet of the year there. And the one over actually on the right is from the comet of 1858, Comet Donati. And for really bright, active comets, you can see all of these individual dust jets coming off the surface. You can see shells and material. You also can see what looks like kind of a bifurcated tail here, where you get material going off. You can see that with Hale-Bopp as well, this bifurcation. And if you remember, that's what we saw with Neowise, especially that first week or two after Neowise popped out of the sun. You had this nice bifurcated tail. And the thinking is that it's just kind of, there's a cylinder of dust being blown back from the nucleus. And like any cylinder, I can even use my glass as an example here. When you're looking through the middle of the cylinder, you're not looking through a lot of material. But when you're looking through that edge, kind of the column density is much higher. It's the same thing that allows us to see planetary nebula as rings, when in fact they're usually spheres. But again, when you're looking through the highest density edges, that's where it's brightest. And when you're looking through the middle, you're not looking through as much. So you get that ring appearance. And that's kind of what we're seeing here. You're looking at a cylinder and you're just kind of seeing the edge of the cylinder. So that's what we think is going on there. Back, 18th century or 18th, 19th century, the thinking was that this was the shadow of the nucleus. Back then, of course, no one had actually done a direct measurement of a nucleus. So you could have believed that the nucleus maybe was 100 kilometers across and it's casting a long shadow. But we've turned out that's just kind of an optical illusion based on that cylindrical effect I was talking about. If you can observe jets, and the image here on the right is from Gianluca Masi in Italy using a 17-inch plane wave, you can actually measure the rotation of the nucleus by the expansion of these jets, or how often the pattern repeats. And so, of course, remember, Neowise was only observable for maybe minutes or an hour or so in either the morning or the evening, so you didn't have all night to sit on it. But Gianluca and others were able to measure that it had a rotation period on the order of 7 or 8 hours, which is fairly typical for a comet. Even though you can see small asteroids rotate, I think the fastest one is 16 seconds or something. Most large objects, asteroids, rotate no more quickly than once every 2 hours. But for these very low density, very weak, fragile comets, you really don't see cometary rotation faster than about every 3-4 hours. And in fact, one of the theories for why some comets actually break up and disintegrate is that they're small nuclei, but they're hyperactive because they've got volatiles and ices that haven't seen the sun in a long time. And so they actually spin up to the point where they spin up so fast that they actually break and fall apart. And that's why we actually see disintegrating comets. Now, you don't just need a CCD or CMOS camera to detect these near nucleus features, whether these jets or shells. I mean, Hale-Bopp was a perfect example. I mean, go back to this image. That's, of course, a visual image. This is a visual image of Donati. But also, you don't need a Hale-Bopp. You don't need a comet of the century or even a comet of the decade. Here was Comet Brightness 46P, which is a Jupiter family comet. An okay size, average size Jupiter family comet, though it did come especially close to the Earth back at the end of 2018, came within about 800ths of an astronomical unit and peaked at around 4th magnitude. But the image here on the right is a CCD image, and it shows 3 jets going off But the image on the left is a visual sketch taken by Michael Taconic using a nice telescope. It was a, you know, a 10-inch Dahl-Kirkham, one of Takahashi's, at 375 power, but he's seeing those same 3 jets that are seen here. And this was another picture taken by Gianluca Masi, and it was taken at the same time and probably within an hour, because this image was taken in Italy, this image was taken in France. And so at high power, you can actually see what you can see with CCD imaging. So you can see quite a bit with these comets, especially the brighter comets, as you turn up the magnification, just like you would if you were investigating or trying to look at a planet, or even look at, you know, kind of low contrast features on a planetary nebula or a galaxy. And then, of course, you know, probably the thing that really excites people about observing and imaging comets, of course, are the tails. The image here on the left is, again, NEOWISE from this summer. This was imaged by John Schumacher. And here's the Big Dipper sitting up here, just to give you an idea of the extent here. So we got a nice dust tail, about 10 degrees long, and then an ion tail that extends almost 30 degrees. Even from this image, there's quite a bit of science that can be done. One of the things is, if you look at this dust, you notice that there's kind of a telltale pattern. It's curving off in this direction. It's kind of curving up into the right. And actually there are programs on there, programs on the internet, as well as you can, if you wanted to, you can dig up the papers and program it yourself. But you can actually predict where you would expect dust to be, or even take an image like this and go, okay, I can actually determine when that dust was released from the comet's nucleus and how large that dust is by where its relationship is with the nucleus, because dust of different sizes is all being blown back by solar radiation forces. Now, gas is really light, so it blows almost directly back. Not exactly directly back, but pretty close to directly back. Boom. The dust is heavier. The heaviest dust is actually more along the comet's orbit. So it's what we call a comet trail. And the lighter dust is moving further back and faster. So you can actually, by looking at images like this, and remember back in 2006, 2007, we had Comet McNaught, which, while it wasn't a great comet for the Northern Hemisphere, that we were able to see it during the day, it was at night an awesome spectacle for the Southern Hemisphere. And you can actually see from those pictures, not only the full extent of the dust tail, but you can tell that you can see individual, almost like little streamers coming off. So you can kind of figure out from the timing of those streamers when individual jets were active. And you can see almost a sort of bimodal distribution of dust sizes, where there were small dust and then not so much intermediate dust, and then larger dust as well. And then when I was talking before about the heaviest material sits along the comet's orbit and produces what we call a comet trail, this picture here by Michael Yeager is actually of Comet 2P Encke. And this line that appears to bisect the comet's actually right here. This tail that seems to be going in both directions, that actually seems to intersect the comet, is in fact a comet trail. It's the heaviest material that is actually populating the orbit of the comet. So what we're seeing here is actually future toward meteors, objects that maybe the Earth will run into in hundreds of thousands of years. But you're actually seeing the comet itself lay down future meteor shower material. Now, what if you don't have a telescope? Well, I mean, of course, for the brightest comets, you don't need a telescope, though a dark sky definitely helps. But comets like that only come around every decade or so. Well, I mean, you can go online. There's plenty of online remote kind of pay-to-play telescope networks, like iTelescope, SLU, Telescope Live. But those, of course, also cost money. Say you don't even want to spend any money, but you still want to do some comet research, or at least just make images of comets, pretty pictures of comets if you want. So it turns out there's a lot of access to online data for professional telescopes. SOHO and Stereo, which are 2 solar observing telescopes. Now, they not only observe the surface of the sun, But in the case of SOHO and stereo, they also have coronagraphs, and that image right here on the right is actually a composite showing ISON as it was coming in and then going out and disintegrating. But there's a nice little chronograph that blocks out the sun, and you can see almost everything within about 8-9 degrees of the sun in this field of view. And it goes down to about 8th magnitude, and it's also kind of cool. You can see the planets go by. Like, okay, the Centaurs, there's M4. Somewhere in here is probably M80, but I'm not sure which is there. But you can also see a lot of, deep sky objects go by. I know right now you can see Jupiter and Saturn, right now being middle of January, Jupiter and Saturn as they're approaching solar conjunction. The stereo spacecraft, of which there used to be 2, but one unfortunately broke, but the other one is still working, also has an imager that not only observes close to the sun, but also goes out 30-40 degrees from the sun. And of course, it's at a different observing angle than the Earth is. It's actually about 40, 50, 60 degrees along the Earth's orbit away from the Earth. So sometimes when a comet is invisible from the Earth, you can see it in the stereo data. And that was the case with a comet that just flew by the sun, Erasmus, which just happened only about a month or 2 ago. And all this data you can, JPEGs if you want to look at. You can also get the FITS images if you also want to do stuff. You can do photometry. And for the SOHO data in particular, not so much for the stereo, but it happens there too. I mean, there are people who look at this data every day and they discover comets. Some of them have discovered hundreds of SOHO comets just looking for these little Kreutz sun-grazing comets that are passing by the sun. Another great resource is the Solar System Object Image Search, which is run out of Canada. And as you can see from the list of telescopes here on the left side, there are a lot of heavy-hitting surveys there, from Pan-STARRS, the NEOSAT. NEOSAT is actually a Canadian small sat that's in low Earth orbit. It's been up there for a while now. I think it's got the equivalent of an 8-inch telescope. And it can get down to 16th, 17th, 18th magnitude. And it was originally designed to look for near-Earth asteroids close to the sun. It never really fulfilled that goal, but it is now being used in some cases to purposely target comets. And so you can actually download a lot of their data. The WISE spacecraft, or NEO-WISE, is there. ZTF, which is the Zwicky Transient Facility. That's the 1.2 meter Schmidt on Palomar, the Ashwin Schmidt. And that telescope is covering almost the entire sky every night. And in fact, the image you see here on the right is actually of 21P Giacobini Zinner, and that was an image taken with the Zwicky Transient Facility. Now, the data isn't always available right away. Like, I did a search just before I gave this, preparing this talk, where I just typed in the NEO-WISE, the bright NEO-WISE comet of last summer. And other than NEOSAT images, there wasn't anything else. Usually there's a proprietary period when these facilities will hold on to their data. But after 6 months or a year or 18 months, then the data all becomes public. So just typing in your favorite comet of a few years ago, you might find hundreds of nice images taken with telescopes as large as 3.5 meters, 4 meters of some of these objects, which are available. So again, if you want to, you don't have a telescope and you don't want to do the remote observing, but you want access to some really great high quality professional data sets, it's sitting there. And of course, it's not just comets and asteroids, it's anything. You've got an RA in deck, you can probably find images of it. So 2020 turned out to be a really good year for observing comets, which was a little bit of a surprise because at the beginning of the year, I will do a podcast for the Alpo where I kind of talk about the next year's comets. And 2020 was supposed to be kind of a boring year. As it turned out, there were 13 comets brighter than 10th magnitude, which gives you a nice indication of how often there are bright comets out there. It's not just the ones that make the news that are kind of hyped as the comet of the century, the decade, whatever. There's always seems to be at least one comet that's within visual range of a small backyard telescope. In 2020, also saw a lot of exciting comets. I mean, we had at least 5 comets that seemed to show some sign of an outburst. 156P Russell Linear, which is the 2 images here. One is a sketch, one is an image. This was a comet that except when it was back when it was discovered back in the 80s, never showed any cometary activity. It was just inactive most of the time. And the next thing you know, boom, it's 9th magnitude. Don't know why. It could be just, it had maybe it had an impact. Maybe there's an active area that activated, or since the comet's orbit did change and it got a little closer to the sun, that was just enough to actually turn it into a full active comet. We had a number of comets disintegrate. The most famous being, of course, Comet 2019 Y4 Atlas. And this one was hyped in the press as the comet of the decade, comet of a generation. And it never quite got brighter in 7th magnitude because it fell apart. And it fell apart when it was still easily observable from most telescopes. But of course, it fell apart at the beginning of the whole COVID shutdown. So in a lot of cases, it was amateur astronomers were the only ones with telescopes who could observe this comet when it was disintegrating. Because I think with the exception of McDonnell Observatory and of course Hubble, everyone else in the US was shut down, at least professional-wise. So here was the best placed disintegrating comet in a decade. And because of COVID, all the big telescopes weren't active. So it was the amateurs who stepped in, who were observing it every night, noticed something was wrong, noticed the disintegration, and were the ones making the observations as this comet slowly fell apart. And it was one of actually 4 comets that were seen from the ground that we observed to fall apart. I did put in a C2020 X3 SOHO, which was the little small Kreutz sun grazer that was observed during the total solar eclipse back in December. And looking forward, there are a lot of nice comets coming, as there always are. Now, most of the comets on this list are short period comets, and that's just because they've already been discovered. We know when they're coming back, we know how bright they are. Long period comets, even in this era of, all sky CCD surveys going down to 22nd magnitude, you're still usually not discovering a long period comet until a year before perihelion, maybe 2-3 years. Now, nothing is expected to be super bright. We don't have a NEOWISE on deck, but maybe we do. In fact, one of the most recent discoveries is C2021 A1 Leonard, discovered by Greg Leonard, who is using one of the telescopes at the Catalina Sky Survey, just north of me in the mountains here in Tucson. That is an object that right now looks like it could get up to 4th, 5th, 6th magnitude at perihelion. But its perihelion is actually really close to the Earth, about 0.2 AU from the Earth. And it's also it's in between the Earth and the sun. So it's at a fairly high phase angle. Now, if you've ever looked at a beam of light or a projector, you notice there's certain angles where you see a lot of dust floating in that beam. And in fact, if you're kind of looking back in the direction of the light, whether that's the sun or the light bulb from your projector, you see a lot of dust. And that's what's called forward scattering. Dust of that size preferentially scatters light. It reflects some back at you, but it preferentially scatters a lot more light forward in the direction of motion of the light. And so if you do have a comet that sits kind of, not exactly between the Earth and the sun, of course, you wouldn't be able to see it, but maybe 20 degrees off that line at a fairly high phase angle, you can actually see that comet's brightness enhanced by many magnitudes. That's one of the reasons why McNaught, the 2006 comet, was so bright. It experienced a 3 to 4 magnitude enhancement in brightness. It shouldn't have been a natural -6 magnitude comet. It should have been only a -2 magnitude comet, but that enhancement helped. So Leonard actually may actually benefit from some of this forward scattering. So maybe it could be brighter. Maybe it could be a 0th magnitude object. It's something to actually watch out for. Or it could disintegrate and let us down, though it does appear to be a dynamically old comet, so it shouldn't be too prone to disintegration. And then finally, just if you're interested in observing comets, want to learn more about observing comets, and especially want to learn how to contribute your observations to various databases. And remember, there's no such thing really as a bad observation. You hear that all the time, and I'll admit I do the same when I observe objects that are a little bit out of my specialty. That my data is not that good, it's cruddy, I can't compete with the great astrophotographers of the world, and so why bother submitting it? But as someone who runs the comet section of the Alpo, all observations are important. All observations are interesting. Even if you feel like your observation doesn't show anything interesting, yours may be the only observation taken that day. It may be the only observation that shows the beginning of a new phenomenon, a new outburst. And I especially like it when people take images that maybe aren't, taken with a 1 meter plane wave telescope, from a subarc second site, just a telephoto lens from their backyard, because quite often that, or even visual sketches, even through a small telescope, that shows what the comet looks to the everyday person. That's what the comet I saw looked like. When I saw Neowise, it didn't have a 30-degree long tail with color and blah blah blah. It was half-degree long tail, maybe a little bit yellow, but that's the comet I saw through my eyepiece. So I really enjoy seeing those kind of observations as well. So hopefully for those of you who haven't observed comets, or maybe only observed the brightest of comets, this kind of piqued your interest to observe a few more comets and to really go a little deeper into making observations that can actually, you can submit them, you can contribute them to any of these organizations, and can also benefit the science and study of comets and even our understanding of what makes these pretty neat objects tick. So thanks for having me.
Well, thank you, Carl. Do you have time for a couple of questions or comments here?
Yeah. Mm-hmm.
Okay. Well, you ended talking about with Neowise and looking at it yourself as opposed to all these great astro photographs. Sometimes the media jumps in on this. We got a great comet coming, and they just love that. And so we go out and look at Neowise, which was a good comet, but to the uninitiated, they look at it and say, okay, well, that looks nice, but it's not, it's not show-stopping. But to us amateurs, seeing something like Neowise, it's really cool. It's really good. And here we are, like you said, standing out with binoculars, viewing this. It's pretty good, and it has quite an impact on you, especially when you know exactly what you are looking at.
Right.
Someone from the media might think, oh, so what? It's not 30 degrees long. But I'm thinking, well, this is really cool. Now, you also mentioned earlier about with Neowise, my wife and I looked at it both in the morning and the evening, and with binoculars. And there we are, slightly defocusing our binoculars on nearby stars to try to get an estimate of the brightness. Of course, I come up with some pretty lame measurements, but it's kind of fun to try that. And the more you do it, the better you get.
Yes.
So that's pretty neat, and it's show that you can actually do something, get something more out of it than just staring at it like everyone else does, hovering there in the night sky. I do have another question on astrometry. Measuring the exact position of the comet in the sky.
Yes.
What part of the comet do you actually measure? You have the coma, which is fairly extended. You're going to have to kind of guess and where the center of that thing is to figure out exactly its correct declination and right ascension. So
Correct.
what part do you actually measure?
So you're trying to measure the center of the comet. So you're trying to measure the brightest part. And the assumption being that's where the nucleus is, because you're trying to measure the position of the nucleus. Of course, you're not really measuring the nucleus. You're measuring the brightest part of the coma. And like when we send spacecraft by comets, JPL usually ran the navigation for those spacecraft, like the ones that went by Temple 1 and Hartley 2. What they discovered, because they're doing astrometry from the spacecraft as well, is that if you've got a nucleus, actually, let's go back to one of my early slides that actually shows the nucleus of a comet. So let's just pretend the sun's over here to the right of the nucleus. So you've got all this material that's blasting off, and it's preferentially blasting off in this direction. So when you zoom out, you would actually see the brightest part of the coma not centered on the nucleus, centered over here, where the most material is. And so you do kind of have this offset that's in there. Now, for most comets, you're far enough away, your plate scale, you're not really resolving.
Well, the actual physical size of the nucleus is what, 10, 20 miles in diameter or something like that.
If that, I mean, that's for a large one. Yeah.
So if you look at the brightest part, you're off only by 10 miles.
Yeah. And so coming back, oop, my astrometry. So this is not actually a great example, just because this is actually the Comet Leonard, the one that could actually become a nice comet later on this year. Right now it's 19th magnitude and pretty stellar. I mean, there is a coma there, but not much.
Right.
But let's find a better image to talk about. This one here. Okay. So when you're doing astrometry, usually, as well as photometry, like I use Astrometrica, which I think maybe a lot of people use for doing photometry and astrometry of asteroids and comets. And you come out and you say, okay, I want to measure everything within a certain aperture. You can't make your aperture too large because it'll start to be kind of confused by the coma itself and will start to be offset from the nucleus because it's going to go to the brightest part of the coma. So you kind of have to use a very small aperture to really kind of nail down exactly. Usually what happens is as you get larger and larger, and this would be a good example, as you get larger and larger, you start getting the tail in there, and the tail starts dragging your centroid away from the nucleus. So you want a really small aperture to center up. But most of these programs, you're not sitting eyeballing and picking exactly, say, the brightest pixel. That's the brightest part. It's doing what's called a centroid, where it's kind of mapping the shape of that inner coma, and it's bisecting it and saying, okay, here's the peak, here's the brightest part that it measures.
Right.
But again, like I was mentioning before, what you're measuring isn't necessarily the nucleus. It's measuring just the brightest part of the coma. So that can usually is offset, used sometimes towards the sun. Sometimes if there's a big tail, it's offset the other way.
Okay. Yeah. That it's a challenge. And as I said a few minutes ago, I bet you that the more you do, the better you get. The better
Yes.
you get at doing it. So that's a lot of experience, and that can help quite a bit. Okay, then. Well, Carl, I want to thank you again for taking your time this morning and doing this for us, showing us a little bit of the world and of comet observations. You covered quite a bit of ground, starting out from how comets are formed, where they come from, how they fly through the solar system, talking about the different ejection mechanisms for the dust and gas and so on, and plus some comets that we have seen recently. Um, Great. As I said, well, thank you again for doing all this. And I want to remind our viewers that this is part of a 75th anniversary of the Astronomical League programs, showing the public and you all what the league is all about, what amateur astronomy is all about, what you can all do. Some of the other organizations, such Carl does a lot of work for Alpo, and he does a lot of, he's from the University of Arizona, so he helps out with a lot of the spacecraft missions on sample retrieval and analysis and all that. So it's a big topic. It's something that everyone can get interested. At least there's something in it that everyone can like, and I think it's really good. And I thank you all for viewing today. Carl, do you have any final words? Would you like to say goodbye or whatever?
Yeah, I mean, thanks for giving me the opportunity to talk about comets, and looks like I will see everyone again in April when I talk more about OSIRIS-REx and asteroid observing.
Excellent. Well, thank you, Carl, and thank you all. We'll see you sometime soon.